We are now ready to start dealing with some probability. So probability is going to tell us the chance of a specific thing, a specific outcome happening. So the first thing that we're going to do is review some of the terminology. I've defined these for you in this individual prep assignment. Pay attention to these definitions. To make sure you understand them, I'll give you some examples as we walk through these. But basically, a probability experiment is any set process where some kind of a chance is involved and we have well-defined results. So for example, if I'm rolling a standard six-sided die, that is an example of a probability experiment. If I flip a coin, that's a probability experiment, right? So an outcome is one of the possible results for a single trial of that particular probability experiment. So if I was to roll a die, what are the possible outcomes of that die roll? Well, if it's a standard six-sided die, that means I have the numbers 1, 2, 3, 4, 5, and 6 as possible outcomes. Now, the set of all of those possible outcomes is called a sample space. So my sample space for rolling one six-sided die consists of the numbers 1, 2, 3, 4, 5, and 6. Good. An event simply identifies a collection of those possible outcomes. So it says, let's say I roll a die, I want to find the probability of getting a 2. Well, that's what we call a simple event because there is only one of those outcomes, one of the possible outcomes that is a 2. All right. So 2 would be the event. Getting a 2 is our event that we're interested in. If I was to roll a die, let's say we want to find the probability that we roll an even number. So rolling an even number, that's my event. But is that a simple event? No, rolling an even number actually means there's multiple outcomes that are possible, right? I could get a 2, a 4, or a 6. So rolling an even number means I have more than one possible outcome that is acceptable. So that would be an example of a compound event. All right, we'll talk about the law of large numbers in a moment. The basic formula for computing probability is right here. You'll take the number of successful outcomes and divide it by the total number of outcomes. We'll use that with some examples here in a moment. But first, let's talk about some terminology that refers to different levels of probability. So first, if the probability of an event is 0, what does that mean? Yeah, there is no chance of that happening, right? So if the probability of an event is 0, that means that event is impossible. Make sense? Let's go to the other end of the spectrum. So remember, probability is always between 0 and 1. All right? So if the probability is 1, what does that mean? Well, we say the event is certain. So if I was to roll a six-sided die, what would be an example of an impossible event? 7. Good. So if it is impossible for me to roll a 7 on a standard six-sided die that just has the numbers 1, 2, 3, 4, 5, and 6. Okay. But what is an example of an event that would be certain to happen? 100% chance of this event occurring if I was to roll a six-sided die. Any ideas? What if I said I want a whole number 1 through 6? And that's my event. The probability of rolling a whole number that's from 1 to 6 is 100%. I'm certain to do that. No other option, right? Okay, so I want you to explore some of these other terms. We already talked about impossible and certain, right? You can label those as the 0 and 1 spot. But here's some other words. Order them along this scale based on what those mean. Okay? And then you guys get to practice doing a probability experiment. Now, experimental probability, also referred to as relative frequency probability, means you're actually going to conduct the experiment. You're going to roll the die, in this case, 10 times. And you're going to record your results of each of those rolls. Later on, I'm going to tell you how to simulate these die rolls on your calculator. But for now, just roll those yourself and just record those 10 outcomes. And then based on those outcomes, you're going to compute a relative frequency probability value. In those 10 trials, what's the probability that you rolled a 1? So you'll count how many 1s you had and divide it by the total number of trials, which is 10, right? Same thing for the number 2, 3, 4, 5, and 6. So just fill those in for your trials. And then answer this question. So how close do you think those are to what you would expect to happen? Okay. And then you need to answer this question. What would make those approximations from your probability experiment of 10 rolls, what would make your approximations be closer to the true probabilities or the theoretical probabilities to what you would expect? Okay, so keep in mind, we're expecting that each of these numbers have an equal chance of happening, right? And so in the ideal situation, all of those numbers would occur exactly the same number of times, okay? But I'm willing to bet that you guys did not have them all occur exactly the same number of times. With only 10 trials, maybe you had 1 or 2 numbers that didn't happen at all, or happened very, very few times. And maybe one of those numbers popped up a lot more often than you would expect it to pop up. Okay, that makes sense. But what can we do to make those all closer? And this is getting into this idea of the law of large numbers. As your number of trials gets bigger, as we do this experiment more and more times, the relative frequency of our event will be much, much closer to the true probability of that event happening. Okay, so let's do this on a larger scale so we can really illustrate what's going on here. Let's pull out your calculator. Here's mine. And we're going to simulate rolling a die, a standard 6-sided die, 60 times. So to find our option, we're going to hit the math button right here. We're going to hit right and go to our probability menu, this 4th menu. And we're going to choose this 5th option, the random integer option. Because again, our possible outcomes for rolling a die are just integer values, okay? And we press enter. And then we feed this 3 numbers. So we, in this case, 1, 6, and 60. So the number 1 tells us what? Right, the number 1 is the smallest possible value, which is a 1. The number 6 is the biggest possible value, which is 6. And that 60 essentially tells us how many random numbers between 1 and 6 I want it to generate, thus simulating rolling a die 60 times. Okay, so if I just pressed enter right now, notice it gives me this result, and the result is actually a list of 60 numbers, but I can't see them all, right? And I definitely can't do anything with it right now. So that's where this store piece comes into play. So if I wanted to store this list in one of my list variables in my stat edit screen, right, I'm going to hit this store button, store, and now I need to put in the list that I want to store it in. So let's just store it in list 1. Perfectly all right. And now I'm going to press enter, and now it generates a list. But if I go to my stat and edit screen, notice my list 1 is filled with those 60 numbers. Okay, so I could actually go down all the way down to 60 right down here. Awesome. So a lot of numbers. And now I could build a histogram with my calculator to see the frequency of all of these happening. So we haven't showed you how to build a histogram with your calculator yet. So let me show you the ins and outs of doing that. So once you have all of your data in the list, in this case our 60 trials, our 60 rolls of a 6-sided die, we're going to go to our stat. So let's quit out of this and let's go to second and y equals and open up our stat plot screen. So we use this a couple of different ways in the past. In this case, just press enter on the first plot and make sure your other plots are off, but turn on plot 1. Now go down to type, and which of those looks like a histogram? Oh, that option number 3 is a histogram. We're going to press enter there. Make sure it's pulling the data from our right list. I put all of my values in list 1. Again, leave the frequency alone. It's just going to stay 1. We're not going to change that. And now I want to graph this. Now, the issue, if I just went and typically we've done the zoom stat, right? Option number 9 on our zoom screen. But if I do that right now, what do you notice? Well, look, there's my regression line from our last lesson. Let's delete that out. Go up and clear it. Perfect. Go back to the graph. But even without that on there, do you see that there's like way more than just 6 bars here? So your calculator automatically chooses the scale for that x-axis, chooses your class width for your histogram, which often is not going to be the right one. I want my class width for each of my bars just to be 1. Okay, so I'm going to hit the window button, and under X scale, that's where I'm going to put in my class width. So I put in a 1 there, go back to my graph, and would you look at that? Now I have exactly the 6 bars, and that's representing how many of each of the die rolls I got. So if I hit the trace button, I can hit right and left, and it'll show me the counts. So for my 60 rolls, the number 1 occurred 7 times. The number 2 occurred 9 times. 3 occurred more than any of them. That occurred 13 times. 11 for 4 and 5, and 9 again for number 6. All right, so theoretically, all those bars should be about even, right? Because each of these outcomes have an equally likely chance of happening. However, they're not. I had one occur a lot more than everything else. I had one occur less than everything else. All right, so what do I do now to make this even better? No, if you were to build a histogram with your just 10 trial version, those bars would have been probably even crazier, right? Well, let's look. Let's do kind of a progressive thing. Let's do a random integer again. But let's just do it with 10 trials. Okay, we store those in there, we graph them, and if you look, well, the number 2 didn't happen at all in my 10 trials. And so all these are a little bit crazier, right? Going back to our 60 trials, No, I'm just storing this over the top of what was in list 1, remaking list 1. No, that version of 60 trials was even more spread out. The number 2 happened a lot. Okay. Well, what do I have to do to make those closer together? Remember that law of large numbers that we talked about? If I increase the number of trials, it should make the variation between my different frequency bars much smaller. And they're all going to be closer and closer together. So how many should I try? Let's see. Let's say we want to try 500. I think 500 could be, let's see, insert a 0 there. Let's do 500 rolls. Nope, we're doing this a lot of times, so it's going to take a little bit longer with your calculator. It'll get there before too long. And we graph those. Oh, well, that's not fitting. So start with zoom stat again. And it's going to make all the bars fit, but now, again, go back to window, change the X scale back to 1, class width of 1, regraph it. Those bars are a lot closer, right? If I hit the trace button, I can go and see that these are happening pretty close to the same number of times. That's a much more level experiment, yeah? And if I go even more, now I don't think this will actually go to 1,000, but I think it will handle 900 trials. So let's do that one. And it should smooth these bars out even more. But it'll take a lot more time to do it. There we go. Oh, zoom stat. X scale of 1. Oh, that's getting really close to level. Every number, 1 through 6, is starting to happen about right on the same number of times. And if I increase the number more, that'll even become more flat. Those will become even more level. What do we call this distribution, by the way? You remember? Yeah, it's getting closer and closer to a uniform distribution because each item is equally likely. Therefore, it should have occur about the same number of times. All right. So there's that. We've talked about making the histogram. Note it pointed out those steps right here in your individual prep assignment. So you have a good idea of what's going to go on. Let me discuss those. So we're going to pause on our experimental or relative frequency probabilities for now. And let's jump to the classic method for computing probabilities. Now, the important thing for this one is the classic method is only going to work if all of the outcomes are equally likely. Okay, so if you're rolling a die, it can't be a weighted die. All of the sides have to have the same chance of happening. Flip a coin, both sides have to have the same chance of happening. Okay, so when we do this, so we already talked about the sample space for rolling a die, right? 1, 2, 3, 4, 5, and 6. So when we're talking classic probability or theoretical probability, we're going to think of, okay, if I want to find the probability of rolling a 1, well, how many of those possible outcomes are a 1? There's exactly 1 of them, right? And how many total possibilities are there? There's 6. So my theoretical probability of rolling a 1 on a single die is 1 in 6. What about for 2? Well, we already said that these events are equally likely, so that would also be 1 out of 6, and 1 out of 6, and 1 out of 6, all the way across for our theoretical probabilities. Okay, now if I was to compute the experimental probabilities from the results on my calculator for those 900 rolls that I did, I think the values that I'd get, so I'd take the frequency of each bar and divide it by the total number, which was 900, I believe, in that last one, right? And I should get a decimal that's close-ish to 1/6, especially as I up those number of trials more and more, okay? Now, your experimental probabilities, especially if you use a low number of outcomes, will typically be quite a bit different than these, all right? The 60 got closer, wasn't quite there. When we ramped it up even more, now those got pretty close. Okay, so law of large numbers is still applying there. So keep in mind our caution here, just because there's only 2 outcomes doesn't mean that the chance of each of those outcomes is the same, right? If I'm out shooting free throws, I probably have a 65% chance of making a free throw right now. I haven't practiced for a while, okay? So I only have 2 possible outcomes when I shoot a free throw. Either I make it or I don't, right? However, I have a 65% chance of making it, probability of 0.65. Missing it is a 0.35 chance. So the probability of each of those is different. So those 2 outcomes are not equally likely. So just to make that aside example, again, for the classic theoretical probabilities to work, all of the outcomes have to be equally likely. All right, there's only one other concept in this particular lesson that we're gonna throw at you, and that's the idea of a complement of an event. So there's several notations that are used in different textbooks for the complement of an event. So you could have a slash over the name of the event. This superscript of a C represents the complement. Just a little apostrophe, a slash there to the side of the event name, or just putting the word not in front of it. All mean complements. So let's do an example. Make sure this idea of a complement makes sense. So here we've defined event A. So this is for rolling a dice. Event A is rolling a 5 or a 6. All right. All right, so what is the complement of event A? Well, that's the probability of not, well, we're not talking probabilities yet, but the event, the complement of event A is anything that is not a 5 or a 6. So what would it be? What numbers are possible? Well, we have 1. Sorry, that was a funky curly brace. We have a 1 and a 2 and a 3 and a 4. Those are all the values, all the possible outcomes that are not 5 or 6. Okay, so if A is getting a 5 or a 6, the complement of A is getting a 1, 2, 3, or 4. So what are those probabilities? Well, the probability of event A, well, there were 2 possible outcomes that would be successful out of a total number of outcomes of 6, right? So I have a 2 in 6 chance, or a 1/3 chance of rolling a 5 or a 6. What's my probability of not rolling a 5 or a 6? The probability of the complement of A. Well, there were 4 numbers that were not 5 or 6 out of 6 total numbers. Make sense? Well, cool. So keep in mind, every outcome will belong to one of the sets. Every outcome of rolling this die is either is either a part of event A or is a part of the complement of A, right? Which means if I add up those 2 probabilities that I just calculated, add up the probability of 2 complementary events together, what do you get? Well, 2 6 plus 4 6 gives me 6/6, which is 1. Okay? So when I add up the probabilities of an event and the probability of its complement, I will always get 1. Why is that? Because I have a 100% chance of having an outcome that fits in either the event or in its complement. That's a big idea, because in a lot of probability problems, especially when we get into more complicated ones, it may be a lot easier to compute the probability of a complement of an event rather than the original event. Okay? And if you know the complement, you can subtract from one and you get the probability of the other one. Okay? So that's kind of a cool idea. So let's jump through these examples. So let's change our probability experiment to drawing a card from a deck. This is a standard deck of 52 cards. Remember, our deck has the numbers 2 through 10. Then it has a jack, queen, and a king, and an ace in every suit. There's 4 suits. So in this case, we're saying that event C is the probability of drawing a face card, a jack, queen, or king. Well, that means we have possible cards that we could draw are a jack, queen, and king for all 4 suits. So there's actually 12 face cards in our deck. Well, what is the complement of drawing a face card? Well, that would be not drawing a face card, right? And what's that probability? Well, if there are 12 face cards in the deck, how many cards are not face cards? There's 40, right? Because 40 plus 12 gives me my total. Okay, so I have 40 cards that are not face cards, so my probability of not drawing a face card would be 40 out of 52. Good? Nice. No, on E, it's letting us know, well, rather than computing that complement directly, I could have just computed the probability of drawing a face card first, which I knew there's 12 face cards, right? 3 in each of 4 suits. So I have 12 out of 52 as that probability. So the probability of not drawing a face card would simply be 1 minus 12 out of 52. And that would give me my 40 out of 52 that I computed the other way. Cool. Very good idea to have a good handle on this connection between an event and its complement. All right, so you guys are ready to go practice what I have preached to you, right? So go work more on probabilities, jump in with your group, make sure you get your questions answered. Have fun with it. You guys are awesome. I will talk with you later.